Thanks for the kind invitation. And I think topic-wise, we move a bit more towards collider physics. So what I will discuss are generators for particularly the Large Hadron Collider, and more particularly about the inclusion of higher order QCD corrections in event generation tools. So as there's quite a low level of time only, so let me jump right into it. So when we look at the LHC event, as you see here, a picture of it, what we can actually describe only very accurately is this very first hard interaction of the two protons that we can solve in perturbation theory. We get very accurate predictions, and usually you have to go to higher and higher order, usually next to leading order, to have something like percent level precision, which is what we are currently aiming for, to really match what the experiments can achieve at the LHC. However, this does allow you to, at most, calculate fiducial differential cross sections, but not really generate such a full event. So for this, what you need is a parton shower, essentially, which includes a parton branching, which at some point form low energy objects and start hadronizing. And on the other hand, these kind of parton shower tools are also allow you to include secondary effects like multi-parton interactions for your underlying event modeling. So all of these things like parton showering, hadronization, and so on are crucial to get a realistic event description. And however, this is done at a much lower accuracy than what we can describe at the hard process level. So what we want to do eventually is a combination of this high accuracy we can achieve at the hard process level with parton showers. Now, when I talk about next to leading order plus parton shower, what do I really mean? So if I have a core process, I want to be next to leading order accurate if I integrate over all extra radiation. If I have an observer with 1 or 2 extra jets, I become less accurate next to and leading order accurate. And what I want to keep is the resummation that the parton shower performs for you. So this would be a consistent next to leading order plus parton shower matching, where you preserve the logarithmic accuracy, and ideally you do not introduce an additional emerging scale, unphysical scale, which you might require to separate different event multiplicities. What I'm not going to talk about is here really how to improve parton showers themselves, their logarithmic accuracy. There has been some very nice recent work, which I will skip here. So let me talk about what methods there are at the moment. And I don't go through much detail again because of time travel, but let me just mention them. So there is originally, like about almost 10 years ago, there was a MiNNLO plus reweighting introduced, and also the Geneva approach and the UNLOPS approach to first apply to very simple 2-to-1 color signal processes. And more recently, we also introduced an approach that I will show you some results of here, the MiNNLO+PS approach, which basically got rid of this reweighting step in MiNNLO. So MiNNLO performs a merging of 0 and 1 jet multiplicities at next to leading order and QCD, and then performs a reweighting to next to leading order, which is extremely numerically intensive. And we were able with this NNLO approach to basically add or include these next to leading order corrections directly in the event generation without reweighting. Now, when we look at the timeline of approach of next to leading order plus parton shower calculations, you see up to 2019, essentially, we have only simple processes like Higgs, Drell-Yan. Higgs Strahlung is essentially also a 2-to-1 process when it comes to QCD corrections, and only really one counterexample, which was WW, which took this reweighting approach to a really extreme, which was extremely numerical, difficult to achieve. Now, this was one reason why we came up with this other approach, this MiNNLO approach, and you will see that in the recent past, if you just look at the last 3 years, there has been really a significant progress, both on the Geneva side and due to the fact that we introduced this MiNNLO approach. So what we basically have now are more processes, essentially all the diboson processes, including W gamma, gamma gamma, ZZWW, Higgs Strahlung, and Z gamma, and maybe most notably even a color process in the final state, or in the initial and final state actually. with top quark pair production, which is one of the central processes at the LHC and very important to achieve next to leading order matching to pattern shorts for that one. So I will flash you now a few results because I don't really have the time to go through the details how these methods work. So let me give you a bit of a small overview what we did with MiNNLO+PS. So first, we looked at simpler processes to the one Higgs, neutral current, charged current Drell-Yan. You see always here, blue is MiNNLO, red is next to leading order for validation purposes. And you see, for example, the transverse momentum of a Higgs boson, fixed order diverges at small transverse momenta, and you need the pattern shower resummation to get a physical result, to get some Sudakov behavior at low transverse momenta. Once you go to high PT, the accuracy of these results becomes only next to leading order accurate, and you see that fixed order and the match prediction nicely agree in this high PT region. If we look at the transverse momentum of lepton and neutral current Drell-Yan, you see again nice agreement at where the observer is next to leading order accurate, and then there's a sensitivity to soft Gluon effects of the fixed order next to leading order correction right at half of the Z mass, and cured by the pattern shower again. Be above this value, essentially you again fall back to next to leading order accuracy, which you see by the increasing bands. So this is all expected, is exactly what you want to achieve. And then if you look for charge current Drell-Yan at the inclusive distribution, you can really validate your result. You see this is inclusive of radiation, no sensitivity to soft Gluon effects, and you have nice agreement within the uncertainties and within a few percent between next to leading order fixed order and the NNLO+PS result. So now there have been quite a few quite a few studies have started to do some applications. So what you see here, just to flash something, a talk by Kenneth Long at Loire, he showed that they used MiNNLO+PS in green here to compare against this very high precision Drell-Yan data, which is a very tricky exercise. And you see, however, that even with these higher order logarithmic accuracy calculations that you see in blue and red, the MiNNLO+PS result agrees reasonably with an uncertainty with this data. Of course, there's only so far you can go with this level of accuracy for this observer. So what we did more recently were more complex processes, like here what you see Z gamma production. So the photon you have to isolate in the final state. So this is a rather peculiar process, and we did a complete validation against next to leading order first, and then we compared against data. You see here the invariant mass of the LL gamma system, so the Z gamma system, and beautiful, nice agreement within really at the percent level. That's both remarkable at the theory and the experimental side, I would say. And you can even see some effects which are missing here, the electroweak corrections that are not included. And we checked if you include them, you also get perfect agreement in these two ways. We performed also this calculation for neutrinos. And again, so here you see an example where you see the decreasing accuracy with higher jet multiplicities. Really only zero jet is next to leading order accurate. And you see a reasonable agreement with data also for the transverse momentum of the missing energy of the two neutrinos essentially in the calculation, or the missing energy observed in the experiment. Then when what we also did was an inclusion of BSM effects on normal circle gauge couplings that you see when you look at the high PT miss region. You can really see what these operators that you include, or this effect that you include what they cause, and you can restrict these kind of BSM effects by even now at the event level, because you are able to produce events and that you can restrict these kind of anomalous interactions. Then, as a last example for color singlets, let me show you ZZ production. Here we went even further than next to leading order plus pattern show. We added a small NQ below correction that is a next to leading order correction to this gluon induced channel, which is formally alpha S cubed. So this is kind of a partial NQ below plus pattern show result if you want. And you see beautiful agreement for this invariant mass distribution of the four leptons at low invariant masses, But once you go to the tail, you know the Electroweak-Sudakov logarithms. And what you really have to do is include Electroweak corrections. This is here simply done by a fixed order calculation. And you see, once you do that, you find again perfect agreement with data. Now, running a bit out of time, let me quickly go over the last thing I want to discuss. So when we discuss heavy quark pair production, the issue we have is that the final states are colored. So you have these color interferences in the final state and final initial interferences. And essentially a resummation formula that everything is based on goes from a simple function, which is really a number, to a complex operator in color space, which includes a Sudakov and so on, and all of these issues you have to take care of. So we solved this issue essentially following this MiNNLO+PS approach. And what you see here is the rapidity of the top quark pair that agrees nicely with next to next leading order again in red and blue MiNNLO, and also gives you a good reduction of uncertainties when going from MiNNLO, so one order higher, lower, to MiNNLO. So the MiNNLO is the black curve here. Now, here you expect agreement, however, with next to leading order. However, for other distributions like the transverse momentum of the leading and subleading top, the fixed order actually has some issues there, sensitivity to soft gluon effects, and you see that you get a slightly better agreement in terms of shape for the leading top maybe, but a clearly better agreement when you look at the PT of the second leading top. Okay, and finally, we looked also at top decays. We actually looked in a recent paper at a number of decays of these top quarks, hadronically, semi-leptonically, fully leptonically, and found essentially excellent agreement throughout all this data, which were, I think, more than 50 or so plots. So let me finish with saying that these calculations are even publicly available in the POIC box. These can be downloaded and used by the experimentalist readily. And let me leave you with my summary and outlook like this. Thank you very much.
Great, thank you. So we're a little bit into the question time, but I think we still have time for one or two. One in the audience. And let me remind everyone, because of the hybrid format, please identify yourself before you ask.
Thank you. Hi, this is Raja Puguzel. How far are we from extending NNLO+ pattern shower methods to processes with jets in the final state?
Yeah, that's a very good question, and it's clearly something which is developed currently. So let me start with Geneva. I think Geneva in principle is already clear it can be extended in the sense that this is based on tau 0 resummation, and you could simply use tau 1 resummation. The same, I think you can say for MiNNLO. So you could use any one jet resolution observable and rederive. I mean, it's complicated work, of course, but you can rederive the formulas with the relevant information. So I would say, in principle, this is feasible within, let's say, a time frame of maybe a year or two, something like this, I would guess.
Maybe one more quick question, if there is one, here or on Zoom. Okay, if not, let's thank Marius again.